Welcome everyone. I'm Mary Cameron. I'm your regional coordinator for the Midlands. Thank you so much for joining us today. This BOHS webinar on occupational hygiene statistics, where we'll be covering the application of statistical concepts and techniques. And oh my goodness, what a turnout. I can't believe this. For the first time since we started these regional webinars, we have hit capacity and we even had to extend it. And if you signed up but you weren't able to attend today, don't worry, because this is being recorded and it's going to be uploaded to the BOHS YouTube channel as soon as we can. So nobody's going to be missing out. I put the huge interest of this webinar down to what an important topic this is, statistics, and of course our fantastic speakers who clearly have glowing reputations to have such a huge popularity for this event. So statistics, they play such a crucial part in testing compliance with occupational exposure limits. We, of course, should always first focus on good practice for any exposure measurement plan. But when it comes to well compliance, how do us professionals do this? How do we account for the variability of exposure? How can we have high confidence when interpreting our results? What impact does a small data set have on this? How can we apply EN 689 and what are its strengths and weaknesses? All very important questions. Well, this is where our speakers come in. We are lucky enough to have not one, but two expert presenters with us today. Dr. Brent Altamas, who hails from Pennsylvania and is a certified and principal industrial hygienist with decades of experience and a particular expertise in the analysis of occupational hygiene data. It's still morning time for Brent, so a huge thank you to him for being so accommodating and starting the day bright and early with us. And also just really quick, just a shout out to Adele McClellan, who is the BOHS Northern Ireland Regional Coordinator, and she put us in touch with Brent. So thank you, Adele. Our second presenter today is Jans Babkovics, who is a certified occupational hygienist and is a final year student completing his master's in occupational hygiene at the University of Manchester. He has a knack for analytical tools such as IHStat, ExpoStat, IHDA, which he will be demonstrating for us today, as well as describing each of their strengths and weaknesses. And we're going to start off with Brent today. If we could all please save our questions to the end, though, where we'll have a Q&A session with both presenters. In the meantime, please do feel free to drop your questions and comments into the chat box. I'm going to be keeping track of these, and I'm going to do my very best to ensure that these are all answered, time allowing. Please also ensure that you have your audio and video off for the duration. If you have a question at the end where you would like to ask it yourself, with audio and video on, that's fine, and you'll be invited to turn those back on. So yes, without further ado, Brent, take it from here.
Thank you very much, Mary, and thank you all for having me here today. We're going to be talking about, I may slip and say industrial hygiene statistics. I will try to say occupational hygiene statistics each time as we go through here. Yeah, I've been an hygienist for actually over 25 years now. It's really been about the last 10 to 15 years that I really got interested in the statistics and data analysis part of it. And a lot of that was because early in my career, I was told a lot of different things about how to interpret data. And I fell into a lot of the pitfalls that are common with occupational hygiene data analysis. And some of the companies I was working with had certain criteria and rules and approaches in place, and they didn't always seem to work. And I got really curious about the different ways of doing the data analysis and what was really the best approach. And so I've done a lot of thinking and research and work around that, and hopefully I'll give you some insight. I've only got about 45 minutes this morning, so I can really only hit the highlights for you, but hopefully it'll get you interested and excited in this if you aren't already. And at least if you're not excited, I realize not everyone's going to be as excited as Jans or myself or Mary might be about statistics, but it'll at least give you flavor for the importance of this in the field. I think someone's not on mute, but so let's start off with just a question to ponder. Just imagine that you've collected 3 8-hour time-weighted average exposure samples, exposure measurements to pentane for 3 different employees. And if we have a workplace exposure limit of 600 parts per million, and we have 3 results that are 290 parts per million, 110, and 205. And just, we don't necessarily, I didn't necessarily want to take the time to try to really do a true polling on this. It's probably just as good for you to just think in your head for a moment. What would be your opinion here if you got these 3 data points? Would your opinion be that you're have the potential to be above the well, that you're below the well, or that you're not sure? And hopefully, we'll come to the point through this presentation at least where you would look at this data and say, well, I really can't be sure that I'm going to be below the well. And the reason for that is there's a lot of reasons for that, but a lot of it has to do with the way a log normal distribution behaves. And if we just pick a few random data points, which we'll talk about, and Mary has her great sweets example, if we just pick 3 random data points, we very well might get data below the exposure limit, even when there are fairly frequent exposures above the limit. So the where I find that we're at today is, despite some of the advances that we've seen in industrial hygiene and occupational hygiene data analysis, more often than not, it seems to be professional judgment that sort of rules the day, where we take a look at the samples, and I've been as guilty of this as anyone. You take a look at the samples and you have a gut feeling of whether they look fine or not. Are they below the limit or not? Do I feel like they're comfortably or consistently below the limit or not? And do they look fine? And unfortunately, that frequently can lead us down the wrong path because, for one thing, log normal distributions aren't particularly intuitive. So kind of the way we're used to data working out, the way we're used to more of a normal distribution working out, doesn't always work so well with log normal distributions, and we'll talk some about that. And because of this, and because folks are not always comfortable with statistics, the statistical tools are often misunderstood and misapplied. So how much data do we need, and what does it tell us? If we had this one data point, if you imagine that this dotted line here is the exposure limit.
Brett, I'm so sorry. Your slides have gone off. We can't. Can you try to put them back on? I'm not sure what happens.
Oh, sure.
Sorry about that.
Let me go back. Maybe I need to try to share screen again.
Yes.
Yeah, I think it might have been that the control was taken off by somebody else who might have accidentally clicked share screen there, because I did see a different PowerPoint very, very quickly. But
okay. All right.
So full screen that again, and we should be.
It was only for like 30 seconds, so we didn't miss out a chunk or anything. But okay, looks good now. Awesome.
Okay, great. Well, thank you for letting me know. I actually saw something funny happen on my second screen, but I wasn't sure what was going on. That must have been it.
Sorry to interrupt. There's an awful lot of people waiting in odd lobbies all over the place still that can't get in.
All right, I'm sure Mary and Lee will work on that.
We'll sort it out. Thank you, John. We'll sort it. Thank you.
Let's plow ahead, and hopefully they can catch up with the recording as well later on. So our apologies for any confusion in the front here. So let's get back to the presentation. So, how much data do we need to determine whether we're below an exposure limit? And obviously it depends on a lot of factors, but if you can imagine that we have this dotted line as an exposure limit, and we have one data point, and maybe it's at about half, and I've sort of intentionally left units off of here. Can we be confident that this exposure group is below the limit? Many of us would probably say no. This one data point, particularly since it's already at about half the limit, doesn't give me a warm fuzzy feeling, so to speak, or a lot of confidence that I'm going to be below that limit. But quite often, let's say we take 3 data points, and now the next 2 data points that I get are pretty well below. Let's say maybe about 15% and 30%, something like that. if I had these three data points, does this make me start to think that most likely, by and large, the exposures in this similar exposure group are below the limit? And myself and many hygienists, without doing a statistical analysis, might look at this and say, yeah, that's starting to make me feel fairly confident that if I keep taking data points, I'm going to get few, if any, above the limit. But unfortunately, the way log normal distributions work and the way variability of workplace exposures work is we really shouldn't have a lot of confidence from these three data points the way they've come out, because there probably is a reasonable chance that there's going to be some data above the limit, even just based on these three data points we already have. And I'll show you kind of how and why that is. Hopefully, many of us already, realize that, let's say these are our three data points and we had several above half the limit, including, one quite close to the limit. I think many of us would say, ooh, I'm a little uncomfortable with that. I probably need some more data. And I would say, yes, you should definitely be uncomfortable with this. These three data points, that there's a pretty high probability that if we keep collecting data, we're going to find exposures above the limit. But even with those lower data points, you don't necessarily have enough confidence yet from the data that you have. So all of that data I just presented you, both the three data points at the beginning and then the random data points below a limit, were drawn from this same similar exposure group, where we fortunately have a lot of data. We usually don't have anywhere near this amount of data for a similar exposure group, but in this case, we have 47 data points. And you can see here that there were indeed some exposures below the limits. Above the limit, although quite a few were below the limit. So if we randomly picked just three data points out of all these exposures, odds are they probably are going to be below the limit. And depending on which day we picked, because if you imagine this is a sort of time series, there are some trends here, it appears. There are some groupings. Maybe this day they weren't really using very much pentane. So if we happen to sample three people all on that same day and didn't realize it wasn't really representative of the whole exposure distribution, we might get a very false sense of security. If we were lucky enough to sample on this day, we probably would have gotten the picture, but there was also a really high probability we'd get several data points even below half of the limit. And if we think that we can just try to pick the worst case scenario, that's a good idea, and certainly I'm not against trying to catch the scenarios where the exposure potential is higher. We have to pick and choose when we're going to sample, and of course we're not going to want to pick and choose sampling when the exposure is likely to be lower. However, our ability to really hone in on and pinpoint exactly when these highest exposures are going to occur is very difficult, because there's so many factors that influence it, including just work practices, which we may not be able to predict ahead of time. So what are some of the things that influence the variability in these exposures? And we may already realize that there are a lot of these potential factors that could influence, but of course there can be process variability that can influence the exposure day to day. There can be seasonal variabilities. Hotter versus colder weather might influence volatility, for instance, of a chemical. There's equipment variability. How equipment is performing, perhaps how ventilation is working, how local exhaust ventilation is positioned, which also rolls into the next part, which is usually the biggest influence, as many of us who've experienced in this field would attest to, is what quite often the biggest impact on variability are work practices. How careful is one person at dumping that powder versus another person, or how careful is that person at positioning the local exhaust ventilation versus another person. And then also their day-to-day assignments can even just vary, their length of time in the area, et cetera. So there's a lot of things that can cause variability in these exposures. And for that reason, one air sample typically cannot estimate exposure. I will caveat that by saying let's not forget about, and I'll come back to this a little bit, let's not forget that our risk assessment is also very important in this. We can't sample everything. So sometimes we're going to decide that there's no potential for overexposure and collect no samples at all, because we can't necessarily sample for every chemical, every agent in the workplace under every scenario. So we have to use some risk assessment to identify what we're going to sample for. And then for me personally, if I'm just collecting a confirmatory sample from something I think is going to be very, very low, I might accept a very few number of data points as long as those data points are low enough. And we'll talk about that. Many of you are already familiar with the EN 689 rules. I'll talk about some of the pros and cons of that as we go along here. So what are some of the tools that we can use? There's these rule-based data interpretation tools such as EN 689. I'll really just, for today at least, primarily focus on the 2018 version of EN 689, but I'll give you a little bit of comparisons of that to some other rules you might use, including the former 95 version of EN 689. And then, of course, there are statistical calculations we can do, what I would call log normal parametric statistics, but usually that's going to be using some data software. You're probably not going to do these with pen and paper. Jans will talk about some of the tools that are available out there, but it's still very important to be able to understand the output and what that information is telling you. Of course, we like to say garbage in, garbage out. You have to be very careful about what data you're grouping together and how you're analyzing it and how you interpret what it means. There are other tools we're not really going to have time to really spend on today, since we only have 45 minutes with me, but there are non-parametric tools, and there's Bayesian statistics, and there's other approaches. At the end, I'll make a real brief mention of some of those approaches. So I actually am a big fan of using some of the rule-based data interpretation approaches. There's a bit of grief over the latest EN 689 2018 version, because I would agree it's quite stringent and conservative, but there's some reasons why the committee that established that went very conservative. And it's still certainly of some great use if you understand what it's telling you and what it means. And the great thing about it is, of course, it's very easy to use, and you often don't need a lot of data to reach valid conclusions. You can just take a few data points, compare them to some threshold rule that we'll talk about, and reach a conclusion. You don't have to use a statistical software. You don't have to do a lot of analysis, and it can be a very powerful tool. Some of the disadvantages, sometimes I think the biggest one is that these rules may either feel very stringent, which they can be, but if they're not very stringent, we may get the answer we want, that the distribution is acceptable, and we are discouraged from collecting further data. For instance, if we had a rule that we had to have 3 data points less than half of the limit, which has been used in many cases throughout the years, that's not a very stringent rule, and we'll talk about why. But if we get the answer we want, we get the 3 data points less than half, we might then be discouraged from collecting any more data, when really there could be the potential for being overexposed within that similar exposure group. So we'll talk about that more, and I'll show you why maybe that is. So most of you, or many of you, may be familiar with the EN 689 rules. This is the 2018 version, but I'll just very quickly remind you or introduce you to what those are. One of the rules is, if you have 3 measurements from a similar exposure group, and if all the results are less than 10% or 0.1 times the OEL, then that would be considered in compliance. And if you take 4 measurements and they're all less than 15% of the OEL, that's acceptable. 5 measurements, all less than 20% of the OEL, that's acceptable. And yes, these are pretty stringent rules, but there's some reasons why they chose some pretty stringent rules here. So if you don't meet these criteria, if you have even one result above 10% from a group of 3 measurements, then the conclusion would be non-compliance unless you can apply a statistical test. And the statistical test would be if you can have at least 75% confidence that less than 5% of exposures in the similar exposure group don't exceed the OEL, then that's considered acceptable. That 5% threshold, what we're essentially talking about is the 95th percentile, and I'll come back to that. But if we're at least 70% confident that the 95th percentile of exposure is less than the OEL, then that's also considered in compliance, and otherwise we're considered not in compliance. Now, something I'll get to is I'm personally not a big fan of using any statistical calculations for less than 6 samples. And the reason for that is, and we'll get more into it, is you really don't have enough data with less than 6 samples to very accurately estimate the standard deviation, or in the case of log normal, a geometric standard deviation, or the 95th percentile. And there's going to be some pretty big error bars, we would say. It's difficult to get a high degree of confidence. But I do agree that if we are going to use a statistical criteria, this is a very good one. This was well chosen within EN 689. I would just argue that perhaps we really should be waiting until we have more data to use it. But I'll show you why. And I usually use 75% confidence. One, it's a little bit more confidence, but also some of the tools I have already set up calculate for me the 75% confidence level for the 95th percentile. So it's basically easy for me, and I don't have everything set up to calculate 70% confidence. But in any case, you could really use either one, and I think it's a good criteria. And I'll show you a little more about that here in a few minutes. So here's a quick example of using the EN 689 rules. It's pretty simple to apply, and that's one of the beauties of it. If I take these 3 data points, the 290, 110, 205 parts per million, I'm comparing them to a limit of 600. I can just divide them by the limit. So 290 divided by 600, 0.48, and et cetera. And then I just compare it. And in the case of the latest 2018 version, are all 3 below 0.1? And clearly they're not. All 3 are above 0.1. So each one, if even one of these was over, and this is where maybe it feels a bit conservative, let's say these 2 were much lower and I just had this one data point at 110, I would still fail the all 3 less than 10% of the OEL, which might give us a little bit of, to use a euphemism, hand-wringing or grief over the rule feeling a bit stringent. But we'll talk a little more about that. But this doesn't meet, and these shouldn't meet. These actually pretty clearly, if you really look at the statistics of it, shouldn't give us a pass. But the conclusion from the EN 689 2018 version would be, I either need additional controls or more data on this exposure distribution. One of the things I could do is I could run some statistics on that. As I mentioned, I'm not necessarily a big proponent of doing statistics on 3 data points for reasons I'll get to, but we could, under EN 689, calculate that 70% upper tolerance limit of the 95th percentile. I'm going to talk about some of these different terms. Basically, all you really need to understand is, for the most part, in most industrial hygiene data sets, usually the thing we're going to look at is the 95th percentile. We could look at other percentiles, but it's essentially a convention that we generally look at the 95th percentile of exposure. And there's a lot of historical precedents for that in science in general and with occupational hygiene data. But there might be reasons to make that more or less stringent at times. But usually we're going to be looking at the 95th percentile. What that means is 5% of our data are expected to be above that 95th percentile, and 95% of our data are expected to be below that 95th percentile. And so if our 95th percentile is below the limit, that's generally considered to be a high enough degree of at least statistical confidence that it's going to be a fairly rare event that we have someone's exposure exceed the limit, although not necessarily impossible. It's almost impossible to ever have a 100% confidence that no one will ever exceed the limit. So we have to choose some sort of statistical criteria. And then also we're often looking at what we call a tolerance limit, sometimes called the confidence limit. This can get a bit confusing. By convention, we're generally talking about tolerance limits when we're talking about the upper bounds of our confidence on the 95th percentile. But that gets confusing, right? I'm saying confidence. But by convention, usually confidence limit means what is our confidence in an individual data point. But I'll just show you. Either way, it's just a different calculation. And if you have the right software, it'll spit out for you the values that you really need for this. So, but I'll hopefully put that in perspective with some charts here. So let's just for a moment step back and talk about these distributions. It's definitely more intuitive for us, and we encounter more often in nature normal distributions. So for instance, here's a survey that was done around 1900 of 3,000 adult male English criminals, and they measured their height, and they very much followed a normal distribution. Somewhere around 5.5 feet. They hadn't started using meters yet in 1900, I suppose. But somewhere around or slightly below 5.5 feet was the average, as well as the median and mode of this distribution. It was pretty well centered around that. And if you go greater or lower, there's a very even distribution of people above and below. If that's the way exposures behaved, it would be a little easier for us to kind of do this gut feeling check of it. But that's not typically how exposures are distributed. Exposures are typically distributed in a log normal distribution, which looks something like this. And so this example is of annual household incomes in the United States, but it doesn't really matter what the example is. It's just to demonstrate for you kind of what a log normal distribution looks like. But I think income is one we can all relate to. And if you imagine incomes in any country, there's going to tend to be very much a left skew in the distribution, right? Where most of the population is at the lower end of the overall distribution, and very few people are at the higher end of the distribution. And we don't even go all the way out here, of course, to the very rich individuals, but it gets less and less, right? But if you imagine just picking 3 random households, it's very likely I'm going to get 3 random households from the lower end of this distribution. And if you imagine Mary's jar of sweets, if you have a jar of sweets with a large number of, yeah, she's holding it up now, thank you, large number of green and yellow Skittles and just a few red Skittles, that's log normally distributed, with the reds being the ones over at this end. And if I just reach into the jar and randomly pick one out, the likelihood I'm randomly going to, now she's going to pick a red. But the likelihood she's randomly going to pick, oh, she did. But that's very unusual. If she does it, enough times, it's unlikely that she's going to get very many reds. Oh my gosh, she must have shaken it up and got them all at the top. But
that has never happened ever. Have I gotten 2 reds in a row? Honestly, I always get a green out of here. This is crazy. Okay, now I have a green. I have a green.
We should have recorded that demonstration so it wasn't so fallible. But hey, that's the way statistics works, is, the rare event can happen. You can indeed hit a lottery from time to time. It's just very unusual for that to happen. And so you can imagine if I randomly pick from a log normal distribution, I'm going to tend to get. And the other thing is, if then I do some statistics around that, I'm going to bias my estimate of the average, the 95th percentile, and the standard deviation. I'm going to bias all of that low because I didn't get the full picture of the distribution, and I didn't really understand the full variability of the distribution. And that's why with just a few data points, typically the calculations aren't going to work all that well. But in any case, so here's just a more formalized version of a log normal distribution, just showing you, okay, if I have data that's skewed left, I use a little bit different parameters. Rather than an average, I use a geometric mean, which is basically a measure where half of the distribution, the weight of the distribution at least, is above, and half of the weight of the distribution is below this geometric mean. And I can still calculate a 95th percentile where 5% of the data is above and 95% of the data is below. But in order to do those calculations, the way it's done is logarithms of this data are taken, and then the statistics are done, and then it's converted back to a log normal distribution. But you don't necessarily need to do that. You could do it in Excel or some tool like that. But there are statistical packages, both free and that you can purchase to do that sort of thing for you. So getting back to this example, I just want to show you kind of how that would work out with these 47 data points of pentane that I showed you. We could use some software or Excel and calculate a geometric mean. That number doesn't necessarily tell us a lot. Although I would say if the geometric mean's more than half, I have some concerns already. But really, that's typically just a parameter we use then to calculate the other parameters, such as the 95th percentile. So I could calculate the 95th percentile. You'll see if I took all this data and did that calculation, I would get the answer, which I already knew just because I had 47 data points and knew that there was a reasonable potential that at times I would exceed the exposure limit. But my 95th percentile of this data is 660 parts per million. And then from this data, I could also calculate an upper tolerance limit. And in this case, I've given you the 95% upper tolerance limit of the 95th percentile. This first number is is my level of confidence, and the second number is what percentile I'm looking at. But in this case, I'm looking at a very high degree of confidence that the upper tolerance limit, the highest it would be 804 parts per million. Either way, we know we're over the limit, but that might help me to decide what level of respiratory protection is needed. For instance, I know that the upper bounds of this exposure distribution are not going to be so high that I need a higher level of respiratory protection, for instance. Okay, so I could also, I'm not going to spend much time on this, but I could also calculate confidence limits on an individual data point. So if I had one measurement, if I took this one measurement of 790 parts per million, I could look at the sampling and analytical accuracy. I would need to get this data from a laboratory or from the description of a method, but I could calculate based on the accuracy the confidence limits around that data point. That's generally not incredibly useful from a overall statistical standpoint. You don't really need to do that in order to do the statistics on the similar exposure group, but it might be of interest if you have just a few data points to know whether an individual data point had a certain degree of confidence that it was above or below the limit. Certainly in the United States, our regulatory agency does this for the data they collect and will only cite folks when the lower confidence limit is above the limit. It's just kind of how their regulation is written. But for our purposes, if I get this data point here that's above the limit, just because the lower confidence limit of that data point is under the limit, my similar exposure group still has a very high probability of being over the limit, and I need to be aware of and do something about that, is my opinion on all of that. So let's just look at some quick examples of calculating the statistics, and Jans will show you some more powerful tools for this. But if I take those three data points, I could calculate a 95th percentile. So if I took the 290, 110, and 205 and just calculated the 95th percentile without any upper tolerance limit, this data would say, oh, my 95th percentile is still below the limit. That doesn't look too bad. I would conclude perhaps I'm in compliance. If I took the 75% upper tolerance limit, now I get 880 parts per million, which is above this 600. Okay, now I'm starting to think maybe I'm not in compliance, or at least maybe I need more data. And then just for an interesting comparison here, if I calculated the 95% upper tolerance limit of the 95th percentile, I get 8,030 parts per million from this limited data set. So the conclusion here would be, I need additional controls. I need a fairly high level of respiratory protection with a fairly high assigned protection factor. And so what's going on here? Why is there such a dramatic difference between these different calculations that I'm doing here? And a big part of the issue here is I just have very limited data with which to calculate these values. So what happens with log normal distributions is, if I just calculate the 95th percentile and I have less than about 9 samples, I'm going to generally underestimate the 95th percentile because of what I talked about before, that if I randomly pick from a log normal distribution, they're probably going to be from a lower end. I'm probably not going to get the full picture of the data. I'm not going to likely get lucky enough to pull 2 reds out of the suites here. And so I'm usually going to underestimate the 95th percentile. And we could show you this through calculations, but and actually I'll show you something here in a minute that may help put that in perspective. And then if I try to take a very high level of confidence, like say this 95% upper tolerance limit of the 95th percentile, that's generally going to way overestimate what the true 95th percentile is, because I just don't have very many data points. There's a lot of uncertainty in it. The way the calculations work out is I'm going to get a very wide range and maybe get that 8,000 part per million upper tolerance limit. And then even the 75% upper tolerance limit or the 70% upper tolerance limit, which I do actually, as I mentioned, agree is a good criteria if I'm going to calculate statistics. It's better, but it still overestimates the 95th percentile for small data sets. So there's still some problems with using it for small data sets. Okay, so before I go to the next slide. So I've done a lot of thinking, and so most of the rest of the next about 8 minutes I have here, I'm going to quickly go through some analysis that I've done, and I don't have time to give it full justice, but I want to give you a flavor. I've done a lot of work over the last 10 years. I've done a lot of presentations related to this, where I was very curious about, okay, what is really the best criteria? If I have 3 data points, is the best criteria this 75% upper tolerance limit? Is the best criteria the 3 less than 10%? Is the best criteria the old EN 689, 3 less than 25%? What really works the best? And how do I decide what works the best? And certainly it may vary depending on the scenario, but the way I started to think about it was to think about the sensitivity and the specificity of the individual test. And so this, unfortunately, I can't spend a lot of time explaining this, but I'll spend a little bit of time explaining this. And I sort of have Mary Sweets on here almost, but if I imagine that I have a disease that I'm looking at a screening test for, which is essentially what we're doing with a statistical criteria. The disease would be, we have the potential for overexposure. The screening criteria is I take a few samples and I make a decision on that. When I have a disease like a virus that I'm doing a screening test for, we're all quite familiar with the screening tests for COVID. If I have a screening test, what I'm trying to do is make sure that I have a test that's sensitive enough that the people that have the virus test positive with the test. So if you imagine that I had, these are our 10 red sweets, Mary, I guess, but you can imagine these are our 10 people with a disease. If 9 of the 10 test positive, that would be a 90% sensitive screening test, which maybe doesn't sound great. And actually for something like COVID, we want something even more sensitive. But the unfortunate thing is, and this is what folks often sort of forget with some of these screening tests, and is typically the more sensitive you make a test, the less specific it's going to be. And we have some pretty good tests out there for medical purposes, but with these statistical screening criteria, this very much holds true. So if you imagine that I have people that don't have the disease, or maybe that there's an exposure distribution that isn't overexposed, let's say I have 20 of those and 12 of them test negative, but 8 of them test positive. So these are false positives. They tested positive by this test, but they really weren't overexposed or didn't have the disease. That would be a 60% specificity. So 60% of the people tested the way they should have, that tested negative that should have. And again, unfortunately, typically if you have a high sensitivity, you have lower specificity. So if I try to make a test that has a higher specificity, I'm going to lose some of that sensitivity. So now my 10 people that should have tested positive, maybe only 6 of them test positive, which would be unfortunate for a virus, of course, or even for exposure distributions. I wouldn't want to miss 4 out of 10 times, right? So that would be 60% sensitive. But now this test I've done much better from specificity. 16 of my 20 that should have tested negative. But the reason I'm explaining all of this is just to get to this next chart, which is a little busy. You'll have this in the recording, and I can send a PDF of this as well. And I actually have a lot more. I have more stuff, a lot more I could have put on here, but again, I only had so much time to talk about it. So So, but and I'll spend most of the rest of my time and then have to cruise through my last few slides, but this is some proof of concept here. If you look at something like, let's just look at the EN 689 rule of you got to have 3 less than 10% of the OEL. This is a very sensitive criteria. In other words, 99% of the time, it's going to fail the ones that should fail. In other words, if you have an exposure, a similar exposure group that has the potential for overexposure to exceed the limit, 99% of the time, this criteria is going to catch that, even with just 3 samples, which is pretty darn good. And is the reason why the committee more or less chose this where it is. Unfortunately, it's also going to fail an awful lot of the ones that should pass. Now, I do have to caveat, I didn't mention, I did this analysis, I've done it a lot of different ways, but this is from simulated data. I've done it with real data, I've done it in a lot of different, but this is from simulated data where the true 95th percentile is somewhere between about half and 2 times the exposure limit. So these are sort of close calls. So this would do even better for scenarios where we're either way above the exposure limit or way below. But for those sort of close calls, we're unfortunately a lot of times going to drive collecting more data. And that was pretty much what the committee wanted to come out of the EN 689, is my understanding. But if you compare this to, say, using a rule of half of the OEL, using 3 less than half of the OEL as your rule of thumb, only about 80% of the time, 79% of the time, 4 out of 5 times would it correctly fail the ones that should fail. That's not great. That means 1 out of 5 times we're saying it's okay when it's really not. So we would have to be very careful about using a criteria like that. You know, we could use some statistics, but as you'll see here, you know, the 75% upper tolerance limit of the 95th percentile, you know, it's actually only 86% specific or sensitive, I'm sorry. Meaning that, you know, 14% of the time it's not failing the ones that should fail. And again, this is just because we don't have enough data to really accurately calculate these statistics. And it's even worse if we just calculate the 95th percentile. We're going to tend to underestimate exposure, and so there's some real issues. If you look at the old EN 689, there were some real issues with this because with the geometric mean rule that was in there, if you're familiar with it, it was a very specific tool. It always passed the ones that should pass, but it quite often didn't fail some distributions that should fail when we had these close calls. So, but I will say the 3 less than 25% from the old EN 689 is actually a pretty good rule. I tend to use that a lot as my own rule of thumb. But the new EN 689 is going a bit more conservative than that. And to me, it really kind of depends on kind of what your risk assessment is what the real answer is. But if you use this one, you can be quite confident. If you had 3 data points, and let's put it this way, if you have 3 data points less than 10%, you can be pretty confident that you're in good shape as long as nothing changes, as long as that was representative of the exposure. It's very unlikely that you miss something with that data. If we look at 6 data points, that's when the statistics start to do as well or better than coming up with some sort of rule for it. So with 6 or more data points, I would generally just recommend calculating, say, the 75% upper tolerance limit or 70%. You could also do the 95% upper tolerance limit, but that's going to tend to be very conservative, as I kind of showed you before. So I only have a couple minutes left here, but then you'll see with 9 data points, I mean, it starts to perform quite well when you calculate statistics. I just want to mention a few more things before I sign off and let Jans take over. Don't forget that a good risk assessment is still going to be key and important to all this. We like to say, you should still engage your brain with the data. Don't just blindly, look at the data and follow the rules and criteria. Those are important so that you understand the statistical probabilities that you could be over, but you also need to, of course, think about how representative was this data? Do I think there are other times when there's more potential for exposure? Or was there something that happened that was an outlier and that might be the reason I need to retest? But also, what is the likelihood of severity of health effects? That to me, that changes how stringent or conservative I want to be. If we're talking about short-term exposure to a solvent that's very infrequent, if it doesn't have any long-term effects, maybe something like acetone or isopropyl alcohol or ethanol for that matter, occasional exposures to that over the limit, while not acceptable, say from a regulatory standpoint, may not have much risk of health effects. Whereas low-level exposure to a carcinogen every day for 365 days a year, like benzene or hexavalent chromium or something like that, I would want to have a very high degree of confidence. I would certainly start looking at those EN 689 2018 rules to give me some confidence that I'm below the limit in those scenarios. Just real quick, I know, well, I think I actually didn't quite go 45 minutes myself yet. I think I may have started at 9:05, but I want to give Jans plenty of time. Just a couple more things I want to mention. I don't have time to really get into this other than to say there are some special considerations when you have censored data. And what I mean by censored data is data below the limit of quantitation for your analytical method. Let's just say, and I have the whole presentation I've done around this, but generally with less than or equal to 5 data points, you're generally going to be best off using those decision rules like an EN 689 to look at your data. There is something called hypothesis testing you could do. We don't have much time to get into that. If you have 6 to 8 data points, you can start to use statistics, but only if you have pretty low censoring. In other words, a fairly low number of the data is less than the limit of quantitation. And there's some approaches like substitution. Perhaps many of you have heard, for instance, substituting with the value, say, the LOQ divided by 2, or maybe the LOQ divided by the square root of 2. And it's actually not that important which of those you use, but it is important that you only do that when you have fairly low censoring. If you do it when you have high censoring, it's not going to work. And I'll give you a quick example of why. If you have higher censoring, you could maybe use a decision rule. You could develop a decision rule for higher numbers of data points. For instance, this might be when having all of them less than half might be useful, because now I have 6, 7, or 8 or more data points. That could start to give me some statistical confidence, and I could do some hypothesis testing around that. But you could also use something called maximum likelihood estimators or other approaches that are a little more sophisticated treatment of the data for this analysis. Well, let me just give you one real quick example of this, why substitution with half of the LOQ doesn't necessarily work. Let's just imagine I had a small data set with 3 data points, less than 0.2 parts per million. If I just plug in 0.1, 0.1, 0.1, I'm going to get a 95th percentile estimate of 0.1. I'm going to get an upper tolerance limit estimate of 0.1, because essentially I'm going to estimate no variability in the data, which is not reality. There is likely variability in this data below 0.2 parts per million. I just don't know what it is. So you have to be careful with just plugging in. With Bayesian statistics, I actually have done a lot of work with Bayesian. I don't know, it's very popular here in the United States. I don't think it's become as popularized overseas yet, but some of you may use this. I'm not a huge fan or proponent of it. It does have some usefulness, but the problem is you plug in a prior probability, and if you're inaccurate in what you plug in for that prior probability, you can come up with some very inaccurate conclusions, and that's about all the time I have to say about that. So just some closing thoughts. Think about that sensitivity and specificity. We give some courses with more detail on this. If you want to message me offline and talk about that. But don't forget about it, incorporating risk assessment into all of this. Certainly for small data sets, I think the rules like the EN 689 are a very good way to analyze the data. Just be aware of how conservative or not conservative the rules you might be using are. And then when you do statistics, something like a 70 or 75% upper tolerance limit is a very good criteria. But I would say generally 6 or more data points is when that really becomes a good statistical parameter. And so with better understanding all this, hopefully you can have a better probability of making the right decision. And hopefully you take a look at this data now and say, maybe I need a little more data to really get a full picture of whether I'm over the work well or not. And there's my contact information. Happy to answer questions at the end, and also anything you might want to call or email me with as well. And with that, I'll turn it back over to, I'll stop sharing and turn it back over to Mary and Jans. I think I hit 45 minutes exactly, fortunately.
Excellent. Perfect timing. You can't hear, but there's a round of applause. Just use your imagination, I'm sure. No, that was excellent. Very detailed. And we'll go straight into Jans.
Okay, just 1 second. Okay, so hello and welcome everyone once again. For those who joined us halfway through, I don't have a slide to introduce myself like the one Brent had. So maybe it's worth to just briefly touch on my background and how I got myself into occupational hygiene and what is my particular interest in statistics. My name is Jan Zbabkiewicz and I'm a certified occupational hygienist. My first exposure to occupational hygiene happened about 10 years ago when I was working as asbestos removal operative. So we had asbestos analysts coming on site to take air tests, and that interested me. So I would spend next 4 years working as asbestos analyst and surveyor. And that's where I got introduced to BOHS. And I realized that asbestos is only one area of occupational hygiene, and there's a bigger world out there. So in 2017, I decided to get myself into a hygienist role. And for the last 4 years, I carried out all kinds of hygiene surveys across the country. I also had a good chance to work on a long-term project for an oil and gas company. So that was where I had a luxury to collect large data sets and work with a large number of samples. And that led me to researching OH statistics. So I'd like to believe I got some grasp of it now. Right now, I'm with Syngenta, a crop protection product manufacturer based in Huddersfield. I still work with, even it's an in-house role, I still work with the limited data sets on occasions. So previous knowledge of statistics is still very relevant. But enough about me. Let me say that I'm very happy to have this opportunity to share with you my favorite data analysis tools. I believe they will enhance your professional judgments immensely. The goal of my presentation is to demonstrate how easy and convenient it is to incorporate the latest developments in exposure data interpretation. First, we will talk about the poor, okay, and good ways to interpret exposure data, and then we'll discuss the best way to work with a small exposure data set. So without further ado, let's get into it. I think many will agree that a good occupational exposure data set is a luxury in the life of a practicing hygienist. Days when large corporations employed in-house hygienists who had time and resource on their hands to collect large data sets are well behind. Nowadays, most occupational hygiene services are provided by consultants, and many jobs are just one-day surveys with a couple of samples. Is it acceptable or not? Well, we'll leave this discussion for another day. So unless you're an academic researcher or an in-house hygienist, you will have to accept small data sets and try to make the best out of them. Direct comparison of collected samples is still ubiquitous nowadays, unfortunately. Some people still directly compare exposure data to some arbitrary limits like 50% OEL, or even worse, against the exposure limit itself. Direct comparison against the OEL would not be that bad if not for the data tending to be log normally distributed. So when we collect a small number of samples, the chances are you collect them from the peak of the exposure distribution curve, meaning that you are not accounting for the tail of exposure distribution. And this leads to a false belief that workers are not at risk, when in fact a significant fraction of workers may be routinely overexposed. So in simple words, a direct comparison of exposure data to exposure limit is not a good idea. A slightly better way exists to interpret exposure data, which is using statistical heuristic to determine compliance. This approach is described in the AIHA book, A Strategy for Assessing and Managing Occupational Exposure, and has some scientific rationale behind it. This approach involves ranking collected samples in ascending order, choosing the median, and then multiplying it by a factor of 2, 4, and 6. So this will provide you with low, medium, and high 95th percentile estimates. If all 95th percentile estimates are below the OEL, it is most likely that compliance is achieved. However, this tool is somewhat simplistic and a more sophisticated approach is usually required. A good way to interpret exposure data is to use a log probability chart to draft a best fit line that will lead you to the 95th percentile. So this can be done manually if you enjoy math and statistics, but you are up for a challenge to find printed log probability charts. The steps are relatively simple. You rank order your samples, you calculate their position on a log probability chart, then you need to eyeball and draw the best fit line to determine the 95th percentile. So it is a precise and robust method to determine compliance. Unfortunately, requires manual calculations and it doesn't account for professional judgment. And finally, the best way to interpret exposure data is to use Bayesian decision analysis. This method allows us to quantify our professional judgment, statistically analyze exposure data, and most importantly, it allows us to combine our professional judgment with the limited exposure data set to arrive at a final conclusion. Such an approach increases confidence and brings transparency to our decision-making process. By the way, Thomas Bayes was an English statistician and philosopher. Unfortunately, he never published what would become his most famous accomplishment. His notes were edited and published after his death by another Welsh philosopher, Richard Price. So shouts out to this gentleman who unknowingly made a huge contribution to the discipline of occupational hygiene. Moving on, let me ask you the following question. When was the last time you used a scientific calculator? How about log probability charts or complex manual calculations? So chances are it was many, many moons ago. It would be fair to say that in our line of work, many of us drive to site to carry out surveys, but I bet you don't contemplate the principles of internal combustion engine every time you turn the ignition. Why would you? If you're just a casual driver who has a little interest in car mechanics and you trust your local garage. In my opinion, same applies to statistics. If you're a practicing hygienist who is just trying to do your best with limited knowledge, but a strong desire to do the right thing, you don't need to fully appreciate the principles of Bayesian statistics. Trusted and validated exposure analysis tools exist to make our life easier, and this is what this presentation is all about. Now, having this background knowledge, we can look into this exposure scenario to see how we could interpret this small exposure data set. The scenario takes place offshore on an oil and gas drilling platform. These men are roughnecks and are responsible for making and breaking string connections, supervising shale shakers, and mixing drilling mud. They all work 12-hour shifts and are routinely exposed to volatile hydrocarbons. On this particular occasion, we were lucky enough and managed to collect 6 samples, ranging from 26 to 176 milligrams per meter cubed. And in this scenario, the in-house exposure limit for oil-based mud is 250 milligrams per meter cubed. So let's try to do it the old way and directly compare results to the exposure limit. All samples appear to be below the exposure limit, so happy days, nobody is overexposed and we achieved compliance, right? Well, wrong. Remember log normal distribution. Chances are we've captured exposures from the peak of the distribution, not its tail. And we will see a true picture when start applying statistical analysis. Probably the most widely used exposure analysis tool at the moment is IHStat, developed by the American Industrial Hygiene Association. It is a simple spreadsheet that is easy to use. What I like about it is that it provides statistical tests for log normal and normal distribution fit. It comes with some drawbacks though. The major one is that it only calculates the 95th percentile with 95% confidence, which is US compliance criteria. So if we want to follow EN 689, if we practice in the EU and UK, the requirement is to calculate the 95th percentile with at least 70% confidence. And it also offers somewhat poor visuals. So in my opinion, it's good for reporting to fellow hygienists, but less appealing to non-OH staff. There are key insights we can extract from IHStat, and these are the confirmation that the exposure data set is log normally distributed, and the calculated 95th percentile with 95% confidence if you are based in the US. So you can see here, the 95th percentile is below the in-house exposure limit of 250 milligrams per meter cubed. But if we want to report it with 95% confidence, it will sit at 1070 milligrams per meter cubed due to the small number of samples, so because of the small data set. And it will significantly exceed the exposure limit. So in this case, we cannot report with enough confidence that the 95th percentile does not exceed the exposure limit, and this means non-compliance. Another tool to consider is ExpoStats from the University of Montreal. I really like this tool because it offers great visuals that can be used in your reports to communicate the risk to non-OH staff. It also allows customizing the level of confidence for the 95th percentile. So we can test for both US criteria, which is 95% confidence, and EN 689 criteria, which is 70% confidence for our 95th percentile. Another benefit is that it allows us to account for within and between worker variations to calculate individual risks. There are some drawbacks to mention. ExpoStats has no function to generate a report, so you will have to manually snip it and paste it in your document. And it also has little patience for you. If you're inactive for 10 minutes, it will reset your data and you will have to type it again. So valuable data insights that we can extract from ExpoStats are visualized exposure distribution and confidence levels for the 95th percentile. As you can see here, the 95th percentile, again, appears to be below the exposure limit. However, when we look at probability levels, we see that there is only a 63.5% probability that the 95th percentile is below the limit. Remember, if we want to follow EN 689 standard, we must have at least 70% confidence in our calculated 95th percentile. So again, this is the case of non-compliance. And finally, we arrive at IH data analyst software that uses Bayesian decision analysis. This software allows us to quantify our professional judgment and combine it with the exposure data to strengthen our final conclusion. It also calculates both US and EN 689 compliance criteria. The only drawback I see is that the free version has limited functionality, but it would be unfair to complain about it. So let's quantify our professional judgment using IH Data Analyst. And we all know that a good survey cannot be done without good observation notes. And my notes from this survey tell me that I could sense a strong smell of hydrocarbons while on site. My notes also tell me that roughnecks were covered in drilling mud. The floor was covered in drilling mud. Walls were covered in drilling mud. And to be frank, drilling mud was everywhere. However, my notes highlight that the activity was taking place outdoors and there was good natural ventilation. The safety data sheet that I inspected also told me that the mud was not that volatile substance. So now I can run a sort of mathematical exposure model in my head to estimate exposure potential based on my observations. And here is my output of my mental mathematical exposure model. I believe, using my professional judgment, that based on observations, there is negligible chance that exposures are below 1% OEL. I give it 10% chance that exposures are between 1 and 10% OEL, 15% chance that exposures are between 10 and 50% OEL, and 25% chance that exposures are between 50 and 100% OEL. What I do believe is that there is a high likelihood, around 45%, that exposures exceed the in-house exposure limit. So I use the IH Data Analyst to enter my values and document my professional judgment. This makes my judgment more defendable and transparent in the future. Now we get to the best part, where we combine our professional judgment with a small exposure data set. Similar to previous analysis tools, the IH Data Analyst tells us that the 95th percentile is below the limit. However, now my professional judgment influences the probability that the true 95th percentile is above the exposure limit. We can see here that after introducing my professional judgment, the probability of the true 95th percentile being above the limit increased from 51 to 65%, while the probability of it being below the limit reduced from 49 to 35%. As you can see, my professional judgment increased the likelihood of overexposure. The UK compliance criterion is not achieved because we cannot tell with at least 70% confidence that the 95th percentile is below the exposure limit. The workplace is non-compliant, and a significant fraction of employees are routinely overexposed. The true picture is now revealed, and actions must be taken to reduce workers' exposure. Now you can see a difference between direct comparison to exposure limit and using statistical analysis. And now I'm happy to do a live demonstration of these tools using another scenario. In this scenario, let's explore it. 4 carpenters were monitored for softwood dust in a workshop. All machines were fitted with local exhaust ventilation. Some visible dust was present on surfaces, but the area was relatively large and had good mechanical ventilation. We were less lucky this time and only managed to collect 4 samples. So let's run them through some statistical analysis and see what the data tells us. Right, I hope everyone can see my screen now, and we'll start with IH stat. So IHStat is Excel-based spreadsheet that is developed by the AIHA and can be found on the AIHA website. It is absolutely free of charge, and if you type in Google AIHA IHStat, first link will lead you to the download page. Good thing about this simple tool is that it comes in 15 languages. For the purpose of this presentation, we'll go ahead with English. And we presented with this screen here. As you can see, I have already pre-typed my collected samples results. So we have 4 samples here. And in case if you need to add more samples, you just need to type them in, and the data will be recalculated accordingly. So we have our exposure limit of 3 milligrams per meter cubed, which is exposure limit for softwood dust in the UK. And here we can see descriptive statistics. So we see minimum concentration, maximum concentration, total number of samples, and other parameters. What I usually pay attention to is geometric standard deviation. So GSD will tell us how much of variability is within our similar exposure group. So if we assembled our similar exposure group correctly, we shouldn't have too much variability within it. So if GSD is around 1.5, it means that our similar exposure group has very little variability. If GSD is 2.5, it means our similar exposure group has medium variability, and GSD 3.5 means there is high variability within our similar exposure group, although still acceptable. What we do want to pay attention to if it's above 3.5. If GSD is 4 or 4.5, that means the chances are you incorrectly assembled your similar exposure group, and you need to consider subdividing this seg into 2 smaller segs. Another statistical parameter to pay attention to here is test for distribution fit. We want to make sure that hypothesis that our data is log normally distributed is confirmed. And for that, this spreadsheet has W test for log transform data. And the test shows us thumbs up, meaning that our data, the hypothesis that our exposure data is log normally distributed is not rejected. So we can apply log normal parametric statistics. So here, what we want to take a note of is point estimate of 95th percentile, which sits at 1.65. And of course, we want to calculate this point estimate with enough degree of confidence. In this case, it calculates 95th percentile with 95% confidence. And when we calculate it with 95% confidence, you can see that it sits at 38.2 milligrams per meter cubed, which is way above our exposure limit of 3 milligrams. The reason why we have such a high estimate of 95th percentile with 95% confidence is because we have very small data set. Brent mentioned that he would not advise to test anything less than 6 samples. But if we still decide to do it, be prepared that 95th percentile calculated with 95% confidence will sit very high. And that is pretty much all about IHStat. And I'll move on to the next tool, which is ExpoStat. So ExpoStat is an online-based tool. Basically, you go on the website and you work. You don't need to download it. You just need to open the web page. And if you type again in Google Expo Stats, the first search result will lead you to this page. And again, what we need to do here is to enter our data to apply statistical analysis. So let's go back to collected data and copy it into data field and change exposure limit to 3 milligrams per meter cubed. So it automatically calculates all statistics while you're typing. And here you can see a cell that says overexposure risk threshold. What it is a cell where you can select with what degree of confidence you want to calculate your 95th percentile. So if you want to apply EN criteria, EN 689 criteria, you want to calculate with at least 70% confidence, meaning that the maximum risk of overexposure is 30%. If you want to work to US criteria, 95th percentile with 95% confidence, the overexposure risk threshold will sit at 5%. So we'll leave it at 30 because for the purpose of this presentation, we want to work to EN 689 standard. And again, we are presented with descriptive statistics here, where we can see minimum concentration, maximum concentration, median. Again, we can see geometric standard deviation. And these statistical parameters here, I'll be honest with you, I don't fully understand how it works and how to use it. But what I do understand is that it represents how well our similar exposure group is assembled. So these data points ideally would be along this midline. But if we have some data points that are outliers and don't really belong to this similar exposure group, they will be further away from the midpoint and they will be highlighted in red. So if we do have some data points that probably do not belong to this similar exposure group, they will be highlighted. And again, we need to reconsider, should we reassign these data points to other similar exposure group? So that is that. And let's go to 95th percentile tab on top, and it does some calculations. And here, if we scroll down a little bit, we have our point estimate of the 95th percentile, which is 1.67 milligrams per meter cubed. And if we scroll down just a little bit more to the very bottom, we see probability distribution of where that 95th percentile is located. So we see that there is 43% chance that our 95th percentile is located between 10 and 50% OEL, and 32% chance that our 95th percentile is located between 50 and 100% OEL. But there's also, I think it's 23% chance that 95th percentile can be above the exposure limit. However, remember, EN 689 requires at least 70% confidence that the 95th percentile is below the exposure limit. And if we sum these two groups together, it comes up to 75% probability that the 95th percentile is in this region below the exposure limit. This is also confirmed here that there is only 23.9% probability of overexposure. The risk threshold is 30%, which means that exposure is adequately controlled and EN 689 compliance criteria is achieved. So if we don't want to introduce our professional judgment at this point, we can declare compliance and report it as compliant. But if we do want to introduce professional judgment, we need to look into IH data analyst tool, which I will talk about next. Few things to mention. Remember, I told about good visuals, and I really like this visual here, which basically takes your small exposure data set and extrapolates it and plots 250 exposures on a sequential plot. And here you can see basically how your exposure would be distributed through the year, let's say, for this similar exposure group. And you can see here where most of the exposures would be concentrated. So the vast bulk of exposure will be below 1 milligram per meter cubed, with some occasional exceedance to 2 milligrams per meter cubed, and very few to exceeding, very few between 2 and 3 milligrams. And there will be some occasions, very rare, when exposure exceeds the exposure limit, but that is acceptable in the eyes of the regulator, and if we follow EN 689 criteria. Same with the density plot, we can see where most concentrations will be located. And yeah, I think that's it for that's all for Expo Stats, and we'll move on to IH Data Analyst. So IH Data Analyst is actually a software that you need to download. It has there is free version called IH Data Analyst Student with some limited functionality. Full version you need to buy a license, but free version, to be honest, is more than enough for me. It does the job, so I can't complain. So here again we have multiple fields that we need to fill out in order to start analyzing our data, but bare minimum is number of samples, concentration, limit of detection, and occupational exposure limit. I pre-typed these parameters and saved them in text format. So I open this file here, and here are my numbers for our exposure scenario. Again, what we can do here is to decide, do we want to base our conclusion purely on sampling data, or do we want to introduce our professional judgment and see how that influences the final result? So if we don't want to introduce our professional judgment, what we need to do is to go to the tab that says BDA initial rating. And what we need to do is to select uniform prior. That means we have basically no opinion about where the 95th percentile lies. We believe that there's equal chance, that the 95th percentile is in any of these categories. So it can be equally as above the exposure limit, as equally as below 1% of exposure limit. So that means no personal professional judgment is introduced. So if we want to do that, we'll leave it uniform and press calculate all. So it goes through calculations. It gives us 95th percentile estimate, which is 1.65 milligrams per meter cubed, some other statistics. But what we are really interested in is in BDA charts, which shows us the probability of where that calculated 95th percentile lies. And as we can see here, there is again about 42% chance that 95th percentile is in the category 2, which is 10 to 50% OEL, 38% chance that it's in category 3, between 50 and 100% OEL, and there is only 20% chance that 95th percentile is in category 4, which is more than 100% of exposure limit. Which means if we only base our judgment on this small data set, it tells us that the 95th percentile is below the exposure limit with 80% confidence. So that satisfies EN 689 criteria, and we can conclude that compliance is achieved. But if we do want to introduce our professional judgment, if we trust our professional judgment, we can quantify it and combine with what our limited data set says. So in order to do that, we would need to go back to BDA initial rating, and instead of uniform prior, we want to select custom professional judgment. So here now we need to use all our years of experience and professional judgment and familiarity of similar exposure scenarios to decide where would we think the 95th percentile could be. So if we go back to that scenario, just to refresh our memory of what we've seen on that survey. Okay, so it's a workshop, so some visible dust was noted on surfaces. However, all machines were fitted with LEV and they all worked as intended. The area was large and there was very good mechanical ventilation. So having these parameters in mind, now I'm thinking, what are the chances of 95th percentile be below 1% of OEL? So think about, I've seen visible dust present on surfaces, so there is probably no chance it's a trivial exposure below 1% OEL. So I give it 5% chance. So I type in 0.05. So here 1 means 100% and 0.1 means 10%. So 0.05 means 5%. What are the chances that exposure is highly controlled? Well, LEV was on site and I observed it being used correctly. However, if that would be the case of highly controlled exposures, I would probably not see dust accumulating on surfaces. So I give it little chance as well, and I say maybe 15% that the exposure is highly controlled. Now I think about, can this exposure be called well controlled? Well, again, we have LEV in place, we have good mechanical ventilation in place, and although there was some dust, it was not piles of dust. So there is higher chance that it's well controlled, and I'll give it 25%. Now I need to think if instead of this exposure being well controlled, is it just controlled? Is it somewhere, is the 95th percentile somewhere between 50 to 100% instead of 10 to 50% OEL? And this is where I give the most likelihood, the highest chances that the exposure is probably controlled. It's somewhere between 50 and 100% OEL. And my professional judgment tells me that there is 40% chance that exposure is well controlled. So that leaves us with 25% chance that, with a 15% chance that exposure is poorly controlled, because I don't think that we exceed exposure limit, but probably we approach it. So this is my professional judgment. Everyone's professional judgment will be different. And as Brent said, professional judgment in this case can influence the outcome. If our professional judgment is skewed, then we can spoil good data set with incorrect professional judgment. So how I see Bayesian decision analysis is that you use professional judgment to confirm what data set tells you, and then you use data set to confirm what your professional judgment says. So it's a constant process of recalibration. So let's see what happens if I introduce my professional judgment to this data set. So we post changes, and again, we click calculate all. And we go to BDA charts. Okay, so it shows us our prior belief, which is our professional judgment. Then again, it shows likelihood for 95th percentile being distributed in different groups for based on what our data set says. And the third chart, posterior chart, shows us the final outcome that is based on both our professional judgment and analysis of exposure data set. So you can see here that the likelihood that the 95th percentile is between 10 and 50%, reduced from 42% to 36%, while the probability of 95th percentile being in category 3 between 50 and 100% OEL increased from 37% to 52%. And this led to conclusion that the probability of 95th percentile being above the limit is only 10%, which means now, instead of telling with 80% confidence that the 95th percentile does not exceed exposure limit, we can tell with 90% confidence that the 95th percentile does not exceed the exposure limit. Still not enough for our overseas colleagues in the US, which often work to 95% confidence. But if you follow the EN 689 guidance, that is more than enough. So in this case, our professional judgment strengthened what the limited data set said. And what I like to do is to write this line in my reports, which is quite reassuring. So based on this analysis, I would write the following. I would write, based on the limited data set and professional judgment, we can assure with 90% confidence that 95 out of 100 days, people will not be overexposed. So that's how we can report how we combine our professional judgment with limited data set. And that concludes my demonstration. I hope you enjoyed it, and I hope that I managed to convince you to introduce these tools in your everyday practice. And if you do decide to introduce them to your everyday practice, I can reassure you that your professional judgment will be enhanced and the quality of your reports will also increase. So that's all from me, and back over to you, Mary.
Excellent. Thank you so much, Jens. That was amazing. Brent, come on back on too, and we'll start a Q&A. We've already gone over though, my goodness. So if everybody is okay to hang on, maybe we could be a little cheeky and kind of get another 10 minutes in there. There's a few questions for each presenter, so we'll go straight in. But I've been so looking forward to this webinar because this is just such a crucial topic. I'm seeing just either not a lot of understanding of the topic amongst hygienists, or just going off of different benchmarks. I mean, some of us are using the 50%, or there's 10% or 25% or 33% from G409, and I just want us to kind of come together and decide what is, the best way forward. And this is exactly what we were just talking about. So perfect. But without jabbering on for too much. Sorry, I'm just getting into the questions here. Here we go. Okay, so yes, a few each for Brent and Jens. I'm going to kind of alternate. First one for Brent. Does Brent think it is better to take no samples at all rather than too few samples? Many consultancy reports only have 2 or 3 genuinely similarly exposed group samples.
Yeah, so of course, a tough question. I mean, I would agree with the statement that it's better to have no samples than samples that give us a false picture of what the exposure potential is. But if those 3 samples, 2 or 3 samples were well chosen, then I think it's always good to have some data. We just need to be cognizant of and careful of how we interpret that, and keep in mind the potential for variability and how truly representative those samples really may have been. So in general, I would say I prefer to have some data when there's any uncertainty about the potential for overexposure. But yeah, if we're going to not use good criteria to interpret them, then sometimes it might be better to not do the assessment to begin with.
Oh, perfect. And let's all remember HSG's 173, which goes through your qualitative tools to begin with, and then you go into exposure monitoring if necessary for COSH Reg 10. And there's many situations which do call for sampling and many that don't. So I'm with you there. Next for Jens, how would you suggest to treat an outlier within your data points?
So if we do have an outlier, we need to try to understand why it is outlier in the first place. One example I can bring is the same with monitoring guys who work offshore. So one sample came back well above, and what I've done is to investigate what happened. So I contacted the lab to see if anything on analytical side, and they did inform me that there was a visual splash on a sample, which could influence the results. But unfortunately, for some reason, they never reported it there on their analytical report. So I had to find it out myself, and that explained a lot. So I invalidated that sample and took it out of equation. But if my investigation would prove that the sample is not sporadic and was not influenced by some cross-contamination, I would think that this person probably needs to be reassigned to a different similar exposure group, or maybe even the existing similar exposure group needs to be subdivided into two smaller groups, and then I would apply statistical analysis to these two smaller groups to see if there are still some outliers. So that would be my strategy.
Excellent, thank you. Right, next over to Brent again. So does the EN 689 standard require randomized sampling, such as when conducting a baseline/comprehensive strategy, or can this be used during a compliance monitoring strategy in which a worst case employee is selected for sampling?
I may actually have to defer. It's been a while since I read through the standard, and I'd have to look back. But from a statistical standpoint, let me just say, a couple quick words. From a statistical standpoint, randomized sampling is very advantageous. If we're not random sampling, then some of our assumptions in the statistical analysis could be invalidated. Now, the rules of, for instance, having 3 less than 10%, those are much less sensitive to any of the bias that might be introduced, unless we really chose the wrong day and they really weren't a worst case scenario. But from a statistical standpoint, if we only pick the worst case scenario, we might underestimate the standard deviation, and our calculations might underestimate the spread of that distribution. So we do need to be a little bit careful about how we interpret that. But at the same time, we have to be cognizant of resources. But maybe Jens or Mary, maybe I don't actually recall if the standard actually requires randomized sampling.
I'm just looking up. I'm sure in the BOHS NVVA guidance it says representative.
Yeah, I remember saying randomized, but I'd have to look back.
I can clearly remember that the AIHA book clearly says that it needs to be random sampling. Well, at least as random as possible.
Right, and that's a recommendation for sure. But yeah, I'm not sure that it's a requirement anywhere. It's pretty tough to make it truly random too. I mean, I guess it's possible, but it's pretty hard.
Okay, we'll shoot on to the next one. For Jens, can ExpoStat be used to help set in-house limits? Based on your presentation, this app seems very suitable. The OH/IH still needs to make sure all this data interpretation is digestible for the clients.
All right, so the question was, can ExpoStats to help to set in-house exposure limit?
Mm-hmm.
Right. It cannot. I might not get the question right, but you can type any exposure limit into ExpoStat. So it's not that it has a selection from UK EH40 limits that you have a drop-down window and you select predetermined exposure limits. It's a free typing field. You can type any exposure limit there. But in terms of setting in-house exposure limit as derived from a no observed effect level, that's not the right, so it cannot do that.
Yeah. Great. Right, over to Brent. So with sensor data, okay to use the detection concentration versus something lower, or is that too conservative?
Yes, that's a good question, and you didn't really have time to get into this too much, but I guess the first thing that I didn't say that's important to understand, if we're comparing to one of the rules, we actually should use that detection concentration or that limit of quantitation or limit of detection, which there can be differences between the two, but regardless, if we're comparing to say 3 less than 10%, we should just take the value that our limit of quantitation was, and hopefully we had a low enough limit of quantitation and all 3 were below that level. And then, that's sort of a moot point. When you're plugging the data in to an analysis and say, using a rule of thumb like dividing it by 2, or some people recommend dividing by the square root of 2, I would recommend using that rather than just plugging the number in for a couple of reasons. Yes, it could be too conservative to just use the value because it's unlikely that the exposure was right at that number. But the other potential problem is, especially if you have several of them, is you may start to bias that estimate of the standard deviation too much. So let's say you had a measurement of 3 parts per million and a limit of quantitation of 1. If I plug in 3 and a couple of 1s, I may really underestimate that standard deviation. Whereas if I had a 3 and a 0.5 and a 0.5, it's a more realistic understanding of the spread. So it's a little counterintuitive, but it actually causes, it's a better estimate statistically if you plug in a half or the value divided by the square root of 2. But again, I would caution against even doing that if you have too much sensor data. In other words, if you have 1 detection and 5 non-detections, you're really not going to get a good statistical calculation out of that. There's other ways to treat that data.
Great. And the next one's for Jens, and it's related. So can ExpoStat handle sensor data, or do you need to handle/adjust it before entering it into the program?
Yeah, a good question. ExpoStat can handle sensor data. No adjustment is required. You just type it in, and it will work with it. It will do calculations. Although the distribution, as Brent said, the more sensor data you have, the less reliable it becomes. So if you start entering sensor data, the distribution curve, the log normal distribution, will start being skewed towards the beginning. So it becomes less reliable. But if it's up to 1/4 of your data set, it will still be very valuable to have it. So no adjustment is needed.
And if you don't mind, I'll just add one thing. I'm not as familiar with ExpoStat, although I'd like to start playing around with that. I do know that the IH Data Analyst, at least the full version that you pay for, will do some, like, for instance, maximum likelihood estimators, which you can handle a little bit more sensor data then and still have it be a valid analysis. So I don't know if ExpoStats can do that, but if it can, that's another way to do it as well.
Great. And then the last one that was put into the chat, I suppose it's for both of you. All the tools shared here, are they suitable for noise exposure data too?
Right. Should I have a go first? I have some opinion on it.
Yeah, and I haven't done as much with the noise data, but I will tell you that I would say no, because the noise data is not necessarily log normally distributed, especially the data as we collect it. We're already using a log scale when we have decibels. So it's not necessarily log normal distributed. And so usually people use dose for statistical analysis, but even that is, in my experience, not necessarily log normally distributed, which is an underlying assumption of these statistical tools. So I think you'd have to be a little careful about that. You could do some statistical analysis, but I think you have to look carefully at whether it's actually normal or log normal, et cetera. I don't know, Jens, what are your thoughts?
Yeah, my thoughts differ a bit. I do use it for noise exposure. Of course, make sure that you delog it first, so you translate it into dose or into pascals as pressure. So don't just start typing in decibels. But what I do find it log normally distributed. I have a luxury to have large data sets for noise exposures, so I can see exposure distribution, which approximates log normal distribution, maybe not as much as airborne samples data. But what I do, I try to analyze arithmetic mean instead of the 95th percentile, because the effects of noise are accumulating. So it's caused by accumulation of energy. So the damage is due to accumulated energy. So the best way to analyze it is arithmetic mean instead of the 95th percentile. So because we're not that concerned that the exposures are on 6 out of 100 days are above the exposure limit value. We want consistently throughout the year to be at low. So we want to apply geometric mean as an indicator of compliance.
Interesting.
Oh, wonderful! You guys, this is all so interesting. There's such a professional judgment goes into so much of occupational hygiene, doesn't it? And there's differences of opinions and different guidance, and you know what's the right one? You know, is there a right one? So this is all. I just love hearing these conversations. But we've come to an end. We're well over time. So shall we say goodbye here and just thank you so much, both you guys. That was excellent. And this is recording. It's going to go on to YouTube. The link will be sent out to those who signed up, who perhaps weren't here at the time. We'll all have access. And let's keep the conversation going. Let's, you know, on the YouTube, there's a chat box. Put your questions in there. We'll get to them. It'll be great to have this discussion carrying on. So yeah, thank you again, you guys. Excellent presentations. Awesome.
Thanks, everyone.
Thank you, Mary. Hey, maybe we'll be YouTube famous now. Yeah.
Oh, you're going to go viral, I'm sure, in a good way.
All right, thank you.
Okay, thanks, everybody. Bye.
Thanks, everybody. Bye.